is we can actually prove that PMI works. And all it takes is the well-ordering principle. So this is a proof I definitely want, you should definitely expect to know. It's a really, really nice proof just using the well-ordering principle. And this is actually what proofs will look like more going forward. Okay, this is not an induction proof. You don't prove induction using induction. That doesn't work. Circular, right? But we can certainly prove this way. So we're proving that PMI as an idea here works. This is cool. So look what I'm doing. I start with the proof of mathematical induction. It starts with this: let n and n be in Z, and for all n, let Pm be an open statement. Okay, so I start by repeating that. Let n and n be in Z, and for all n greater than or equal to n, let P of n be an open statement. So I just straight up copied that, because that's the law of universal generalization. I need some actual letters and general things to work with. I want to prove the conclusion here. Induction is one big if-then statement. If 1 and 2 are true, then conclusion for all n, P of n is true. So it's a big if-then statement. How do you show an if-then statement? You assume the if. Assume the if part. Just like I mentioned a second ago, I'm going to assume that 1 and 2 are both true. Step 1 and step 2 are both true here. Assume that both P capital N is true, and for all k greater than or equal to n, pk implies pk plus 1 is also true. For all k greater than or equal to n, this is always true. Okay. Now, the trick to this proof, I need to show that for all n greater than or equal to n, Pn is true. What I'm going to do is I'm going to let F be the set of things that are false, the set of statements that are false, or more specifically, the set of integers, n and z, where n is at least capital N, and Pn is false. Okay, so I'm looking at the set of the actual statements where it's false. Now, if induction is going to be true, this should be the empty set. Okay, but we have a proof by contradiction, basically. If this is not the empty set, if there's something in here at all, well, then by the well-ordering principle, notice this is a set of integers. And in fact, yeah, it's a set of integers bounded by below, bounded from below. They're all bigger than or equal to capital N. So we have a set of integers bounded below. That's the well-ordering principle. This thing must have a least element. F contains a least element, and I just called it L for least. Well, since P of n is true, we know that L is strictly bigger than n, right? Because we assumed right here, P of n is true. And so if P of capital N is true, then capital N can't be in this set. This is the set of all little n's where P of little n is false. So at capital N, P of n is true. So that's capital N is not in there. Since P of n is true, we know L is bigger than n, and thus L minus 1 is greater than or equal to capital N. Hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So if you're taking a university, if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example. Right? On the number line, we have capital N here. And what we know is whatever the smallest thing in this set is, it must be over here somewhere. It can't be at capital N. It can't be at capital N. The lowest thing that actually works here, which we called L, oops. There's my L. It must be over here somewhere. It has to be strictly bigger than N. It can't be n itself, because we know n itself is not in there. Maybe it's the one right after n. Maybe it's n plus 1, capital N plus 1, but it's at least after it. But now that we know it's after it, now I can look at the point. Now I can look at the one that is immediately behind it. Come on. My selector. Oh, can't do that. All right. Immediately behind it is L minus 1 on the number line. And if L is the smallest number in the set F, if L is the smallest number in the set F, and that's what this is, a least element in the set, then L minus 1 is not in the set. And if L minus 1 is not in the set, then that tells me that P L minus 1 is true. Right? PL minus 1 must be true because L minus 1 is not in the set of indices where it's false. No, well-ordered principle doesn't need to be in Z plus. It just needs to be in any set that is bounded below. So I can have the set of integers where as long as I can have the set of any integers I want as long as they are bounded below by something. It works the exact same way. So if all my integers are above negative 12, well, then any subset of that will contain a smallest element because the worst it could be is negative 12.
Hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe. I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example.
So PL minus 1 must be true. PL is false, but PL minus 1 must be true. And that's a contradiction because look what we've got. We've got that for all k greater than or equal to n, and this k would work, k for L minus 1 would work, pk implies pk plus 1. So therefore, PL minus 1 implies PL. That's the contradiction. And say, yes, n is the bound. PL minus 1 would imply PL. Because PL minus 1 is true, therefore PL must be true. But we had PL is false. That's the contradiction. By the inductive step, we have PL is true, which is a contradiction. N is the bound. N is the bound. N is a fixed number. Capital N is a fixed number. Whatever it is. N might be negative 12. N might be 37. N might be negative 1,000,000. It doesn't matter. N is the starting point, and then everything after that is to the right of it. So on the number line, whatever it is, everything after that, everything on the number line is to the right of that number. Okay? And so my contradiction was this. I started by assuming or asking if F is not empty, then I get a contradiction. So the only result left is that F is empty. Thus F is empty, and thus everything is true. Nothing's false, and we get the result. So the logic goes like this: if induction didn't work, assume you've got both a base case and an inductive step. And if it doesn't work, then there is a first situation where it doesn't work. There is a first n where it doesn't work. So in the first example we did, this thing here, if this is not always true, then there is an n value, which is the first time it's not true. Right? It works for 1, so that's not 1. So there is some first value of n, we'll call that L in the other example, where if I take the sum of the digits from 1 to L, I don't get L times L plus 1 over 2. But the inductive step, what we proved here, was that if it works for some k, it must work for the next thing. Well, in the situation I just laid out, I assumed it does not work at L, and that's the first time it does not work. But then the consequence of that is it does work at L minus 1, the number immediately before L. If it does work at L minus 1, then I apply the induction hypothesis, and I get it must work for L. And that's the contradiction. It doesn't work for L, and it does work for L. So my assumption was there is a spot where it fails to work at L. I get a contradiction when I do that. Therefore, there is no place where it fails to work. It works all the time. Okay, that's the logic. Go back and watch this recording if you need to a few more times to get used to it. But that's the idea of what's going on there. Okay, very nice little proof using the well ordering principle. Definitely worth understanding that.
Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So, if you're interested in really understanding this content, getting a good grade because you understand the content, go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.